All right. Very happy to be here. My name is William Wen. I'm from University of Michigan. I'm an associate professor at Department of Biostatistics. So today I'm going to talk about Bayesian integrative analysis of genetic association data. I understand only a small proportion of the audience familiar with this specific topic area, so I'm trying to keep the material light, especially late of the day, so less technical, more like intuition. Hopefully give you kind of a thought process why we take, especially the Bayesian type of the approach to tackle this problem. So I take the liberty to kind of summarize the talks this whole week. So there's kind of for a statistician, I think, can summarize there's different challenges, statistical challenges. So if I may, the first observation is there is a lot of integration of multiple data sets, right? I mean, it's the same type of the data or multiple data, multiple different types of the data. And account for uncertainty in analysis is always kind of a essential issue. Can you say something with a quantification of uncertainty? The third one is kind of a consistent theme. We as data scientists or statistical analysts will always be facing this kind of a dilemma. We can build a very complex model, but not be able to fit it. Or we can take a computational approach, but cut some corners. So the real good analysis, in my view, is kind of take a balance between the two issues. Hopefully, we'll show you some of these examples. So as I said, my particular interest, scientific interest, is statistical genetics. And nowadays, we are dealing with multiple types of genetic data. So the kind of the general theme for this talk, or you need to understand, is we're trying to integrate the knowledge learned from different sets of genetic association data. They could either come from molecular phenotype or complex phenotype. So like Bogdan's talk the other day, there is sort of like integration of the knowledge and the integration of the data sets. So I'm trying to make a point. So the integrative analysis always has two, in my personal view, like two different goals. One is trying to kind of understanding or elucidation of the underlying molecular mechanism of complex disease, right? We know that the DNA impact RNA and then impact the complex traits. That's kind of a very naive biological model. But can we fill in the details in this kind of a simple causal model? The other thing is more kind of the second bullet point is more clinical driven or the application driven. Can we do better prediction based on one's genetic information? On top of that, we may throw in functional genomics, the data. So my point is these two different tasks are kind of a different analytic tasks. They are different types. The first one would emphasize a lot on uncertainty quantification, right? So the usual task you do for elucidation or understanding molecular mechanism, you probably deal with a lot of hypothesis testing. So you kind of, there is kind of a statistical rigor required. You're not allowed to make a lot of type 1 error, right? I mean, the false positive is really kind of hated in the first task. The second task is different. It's more like machine learning, the general covered by the general goal of machine learning. So you need to make a prediction, and then your prediction is judged by your, it's actually evaluated by your loss function, and then maybe in the in practice, how do you judge it is from the practice. So different goals, and then we may end up with different kind of statistical approach. So just a note on that. So lastly, just before we get into the specifics, why Bayesian? So every year I'm trying to give you a different motivation why we should use Bayesian. This year, let's do from a consumer point of view. Okay, so you are in charge of analyzing, let's say, the EQTL data. You need to kind of deliver the analysis results of these EQTLs to the community. And you need to play the role of a member of community and then let me know what kind of the results you want from genetic association discovery. Okay, so you may have already thought this problem before. I will just tell you a little bit kind of our thoughts on this. So the most maybe it's safe to say obnoxious thing in genetic association analysis is LD, right? You gave the most significant SNP. Sometimes it's not really characterize the full nature of your analysis. So that's the key thing. So we argue there are two different levels of information you can provide to the user. One is either the certainty or uncertainty of the existence of independent association signal. So this question is more about if I tell you there is chromosome 1 and a certain position in that particular locus, in that terminology, is there association signal? Is there EQTL live there? So the existence of that signal. The second level of the question is you want to know, we argue, there's which SNPs are responsible, causally responsible for that signal. Because of the LD, we'll see an example just right after this. You may not be able to confidently say this particular SNP A is causal, SNP B is causal, but you may be able to say this set of SNPs are potentially causal to this cluster of, and then they are responsible to that single association signal. And then you need to quantify for each individual SNP their individual uncertainty. So uncertainty play in different kind of levels. So that is kind of a natural hierarchical representation of the association signal. Think about this. Once you determine there is a signal exists, all right? I mean, that could be represented by a few SNPs in LD, okay? And then you can further kind of quantify which SNPs is responsible for that signal. So if that's still vague to you, let's just consider a very simple example. And then I play, like in statistics, always say there is an oracle. And then I'm going to play that oracle and say there is two perfectly correlated SNP responsible for a single genetic association. They are perfectly correlated. I know that. And then I also kind of tell you these two SNPs, let's make the problem even simpler, like in completely in linkage equilibrium with the remaining of the genome. So you know, so one of the SNP going to be responsible. The key point here is, based on the association data, you will never know which one is causal, right? So how do you report the results? So based on the discussion we had, I would argue the logical thing is to say the probability of existence of an association signal in this case is 1, right? Because we know one of the two is. So think about in that signal cluster case. So the probability for that signal cluster is 1. And at the individual SNP level, they are indistinguishable, unidentifiable. So at the SNP level, each of them get 50% of the probability. So this is a kind of a maximum degree of uncertainty. But you know, when you actually present your results in this form, this is more informative, right? You know where the certainty is, right? There's the existence. And then you know where the uncertainty is. The LD will cause the maximum degree of uncertainty in this case. So this is kind of a simple toy example. Hopefully you understand what we're trying to do. So in short, we're trying to basically build a mapping program, multiple SNP genetic association analysis program to have this feature. Not only tell you which SNP level uncertainty, also tell you at which SNPs are come together, they're responsible to a single cluster. So how do we do that? Before we do, there's also kind of a benefits of a probabilistic representation in the difference. So I actually forgot my punchline. So if you use this, this kind of probabilistic quantification, then it seems like very natural you pick Bayesian as your tool, right? I mean, to perform the inference, and then so that's actually my punchline. So so the benefit of using before okay, so just go directly to the second point. So it actually has this posterior probability. It allows you to do very rigorous force discovery rate control. So if you're not familiar with force discovery control, so in the field, in practice, it's mostly carried out by calculating p-values. But so Afron is the first one actually proposed these using this so-called local FDR. So in the actual form, they're nothing more than the posterior probability. And then in our recent kind of a little bit relevant work, we kind of connect these two things, basically saying if you have a p-value, and then at the same time you have a sort of under certain conditions you compute a local FDR. So you do the FDR control, you actually get identical results as long as the sample size, I mean the number of the tests is large. So that's kind of a peace of mind, and you don't really need to go to the p-value to do FDR control. You could, even you get the Bayesian part, the posterior probability that still enable you to do FDR control. And then the third natural thing is you could construct a so-called Bayesian credible sets. So this is basically the minimum sets that's responsible to that signal, like we discussed. So let's talk a little bit about the technical term. But so we're going to use a very simple model. So this is a linear regression model, and commonly use the invariable selection problem. So you have a complex trace vector y, and then you have a p variable for candidate for the candidate SNPs, and you add a kind of a residual error term. So this is the white noise added on top of the genetic signal. So just to make the problem clear, we kind of define this latent binary indicator. You don't have to define this, but define this is to make your goal very, very clear. You're actually trying to identify the non-zero, or there's SNPs has non-zero genetic effect, right? I mean, that's nothing more than that. And then the real interest of this is just jointly infer the whole vector, the p binary vector of gamma, right? So on this framework, it's very easy to, I would say very easy, but at least at the modeling stage, to incorporate genomic annotations. You have seen through a lot of talks, through a logistic prior. So if you can say a priori, based on this genetic annotation, I can build a different prior for different SNPs, possess different functional annotation, right? And if you don't have that annotation, you don't need to worry that everything is zero, so everybody has alpha zero. So this is the case we call the exchangeable prior. So every SNP is equally likely to be the causal SNP. And finally, we have this just to show a priori all the SNPs are independent. At least being a causal SNP is independent. This is not a very complicated model, and then almost everybody uses this. So a few things, if you want to do inference from this, actually the biggest hurdle is computation. Why? Because actually the so-called marginal likelihood or base factor with respect to gamma is within just basically the ratio between a particular gamma to gamma equal to 0. There is no SNP associated. This one has a closed form in quantitative traits at least. So that means you can analytically do the analytic computation for that. And then if you apply the Bayes rule, all you need to do is compute this quantity, this posterior probability for the gamma given y, that's the complex traits, and then the g. And then the calculation is the probability gamma, that's easy. That's the prior, right? I mean, this is a logistic prior. You should know how to do that, to do the computation. This one is analytically computable. And then, so you just sum over all possibility, that's it. So it sounds very easy, I just go through that. But it's impossible. The key difficulty here is you are not able to enumerate all possible gamma values, right? I mean, if you think p, and then how many possibility of gamma prime here going to have is 2 to the p, and then it could be go ugly very, very fast. So we're dealing a problem for eQTL mapping. On average, we have thousands of SNPs. And then in some extreme cases, we may have 20,000 of SNPs. So it's impossible to enumerate all the possibilities. So if you want to use Bayesian, you have to think about approximation, right? I mean, you could just give up right here and say, OK, there's a model I cannot fit. But I mean, for people like persistent, you should think about some like approximating method to do that. So a general solution to do approximation in Bayesian to deal with this non-normalizing constant, this is using MC algorithm. So that algorithm is kind of a theoretical guarantee no matter how large this term is. If you run your chain long enough, you get converged. But the problem with that is practically, I think we don't know how long is long enough. And then a lot of people run MC ends up with the chain is not converged. And then you get some results. It's really not that great. So, the alternative solution, we call the deterministic approximation of posteriors. So it's a rather simple idea. Instead of calculating this whole thing, we take this view that in general, there are very few the truly associated signals, right? So therefore, the contributing model to this term is actually much less than 2 to the p. So if there is a function, kind of a fundamental way, you can construct this subspace which has high probability model, high posterior probability model, I should say, and then you are better off just approximate this term with this, and then you can estimate the probability mass you admitted, ignored at this point. So that's really the simple idea of the DAP model. So the principal way to construct this kind of omega space is based on actually a frequentist principle known as Shor independent screening. It's nothing more than this running the marginal testing and then the conditional testing and then find the good models. And it turns out to be very practically efficient and help us to evaluate this term. But this is our kind of a previous work here, if you're interested. But still, this posterior doesn't have this kind of a desired property, right? We want the cluster level thing, and then we want the cluster level quantification, and then we also want the SNP level quantification. So if you fit this type of the model, you summarize from the posteriors, you get SNP level like everybody else, like MCMC, but you don't really get the cluster level, that signal cluster. That's really nice to have. So the key idea is you can further constrain this omega with this kind of a signal cluster structure. So it's kind of a saying, there's the omega has to come up with this one cluster, second cluster, and third cluster. And then the models in this is kind of a combination from different clusters. Kind of an intuition in this kind of a construction lies in these two things. So the SNP in the same cluster has to satisfy this condition. One is they are somewhat in LD. That has to be true. I mean, that's there's nothing to argue against for this one. I think everybody accepts that. The second part is actually the interesting part, and it's actually very intuitive. So the notation here is I don't know if you can see this, there is an I bar. That means the I. So if I consider two SNPs, are they in the same the cluster or not? The I bar means I is not in I is 0 in the gamma, and then J is not 0. So that means including the model currently including only J. Okay, so the second term is the model currently only including I, but all the other but besides these two SNPs, everything else holding the same. I'm not saying there's only one SNP is associated. You're understanding the difference between this configuration versus this configuration, they only different on one SNP. In this case, the J is 1, and I is 0, but in this case, I is 1, J is 0. So the point of this is you're including one of this SNP, they're kind of a redundant, right? They are kind of a same representation of the same signal. So they should give you the same sort of approximately same, the posterior score. There's a non-unnormalized, the posterior probability. However, the key point is if you put two things, both things into the model, you will see a dramatic drop of the posterior probability, at least for the unconstrained one. Why? Because if the SNP corresponding to, the two SNP corresponding to one signal, you included both of these into the model, it doesn't really increase the likelihood. So this part is similar as before. But the prior here, remember we have independent prior. Every time you have a SNP you label as included, you're going to multiply by that prior. The prior is a penalty, right? It's usually very small. That means if you multiply this quantity and then your likelihood doesn't really change, this term is going to be much smaller than the other two terms. So this will give you a hint that these two SNPs, they're in LD, and then they have a redundant kind of a representation of the signal. So this way will guide you through and then help you to find that signal cluster. So it's just the intuition behind this algorithm. If you do that, you put the structure into the omega, and then you can have this signal level posterior inclusion probability. It's simply just the sum of the SNP level posterior probability as long as they belong to the same signal cluster. And then it is guaranteed that this is a valid probability distribution, meaning it's bounded by 0 and 1. And the even better thing is 1 minus this, the SPIP, become the local FDR for that particular signal cluster. Now you could do this, the FDR control for the local cluster across. So you basically have this statistical device, you could test to control your force discovery rate on the signals. And also, this is also very naturally, you can see that you can construct an alpha % credible set. So you want to construct 95% credible set for every signal, but you need to keep in mind, not every signal have a 95% posterior probability. Only the signals that quantified as strong as 95%, you can have a 95%. Otherwise, it's up at, to the point that this SPIP value is. Yeah? Hopefully that's a clear point. So, so we also kind of work on this problem, the inference with summary level data. It's actually, we're quite late to the game. I think the people in this room made a tremendous contribution to this problem, but we thought that nevertheless, I think we should have, the software should have the ability to work with the summary level data. So the commonly used, the problem with the genetic data is because privacy concerns, you don't really get individual level data, like the Y and then the G. What you get is kind of all in the form of a summary. So, so these people, I think, hopefully that's a complete list. There's a lot of them sitting in this room. So to start from a very practical point of view, like we only have the z-scores from single SNP analysis, and then we only have the correlation information learned from an LD panel, then we could actually, well, and it's a very creative way to say that we can use it to do multi-SNP analysis, right? That has been the prevailing approach is in the field. So here I said the Z is the Z-score, R is the correlation matrix, just the characterization of the LD. So it turns out, so we kind of study this from a different point of view. We kind of are trying to say there's a principle called the data reduction principle in statistics. So the principle is very easy. There's how can you reduce your data into certain like functional forms until you can still do the get the same inference results as before, right? I mean, if you could do that reduction, you should reduce your data into that. So we use that principle to examine this, to ask the question, is this the best practice? I think it turns out to be, it is sufficient, meaning there's give you the one-to-one mapping between the summary level data and the complete data, that means summary level data, and then the, say it again, so the individual level data and then the summary level data, if and only if you know the variance, the residual variance. Otherwise, there's a little bit, they will yield a conservative results. So what happens is actually that take away your ability to actually re-estimate the residual error variance when you have a multiple SNP in the model. So that's just what happens. So usually that means added noise level, and then you get lower or smaller the signal noise ratio. So it turns out you need to add a few things back to recover this ability to estimate tau. So now is instead of a Z, you need to have the beta hat, a standard error beta hat. Become two vectors, still need to have R, and then you need to have some information from the quantitative traits. The SST is simply the sum of squares, it's just a number. N is just a number of individuals. So you just need to trust my word. If you do this, that give you back the ability to recover the tau, and then sometimes you do a little bit better than using the ZNR. So just to show you the performance, we do the simulations. So to make the simulation more realistic, we kind of artificially construct this type of the LD blocks from the real data. We ends up like 91, 11 SNP. Don't ask me how come we are with this kind of odd number. We actually made a mistake. But we actually want to do 110 SNP, but somehow there's a mistake in the code. It's end up with this odd-looking combination, but still works. So we simulate the quantitative traits trying to match the z-scores you observed in the real the EQTL studies. And we're trying to assess the ability of different approaches, especially the multi-SNP analysis approaches, to identify the signal. So we only throw one SNP per as a causal SNP in each LD block. So we're trying to so naturally this is a kind of a constructed, artificially constructed example. So if you identify as the signal, the whole signal cluster very naturally will be this 11 SNPs, right? So we do comparison with this kind of a state-of-the-art MCMC program called a FineMap. It's actually use summary level statistics from Z statistics, and then they use the and then R. That's the correlation. So I'll tell you the few things. So this is kind of a ROC curve, but constructed in the meaningful range, because this. So the right line is you using the program we call this DAP-G, running on the simulations with we call the sufficient summary statistics. That means the statistics including some SST and then beta hat, standard error beta hat. So the green one would be the same DAP-G program, but using only Z value and R. So the difference between this line indicating there's the information loss by losing the ability to re-estimate the residual error variance. And then that's pretty anticipated because we do throw multiple signals into multiple blocks. So in that sense, it's important to kind of re-estimate the residual error variance. Is kind of an important thing. So this green line and then purple line is the DAP-G using the Z and R. This is kind of a minimum summary statistics versus the FineMap. So it's an MCMC algorithm. So it's actually interesting because they calculate the base factor or the likelihood exactly the same way. They all kind of it's first derived by Eliezer, and so the difference here, actually the priors, the FineMap is actually assuming a better version of the prior than ours, especially for the simulation setting. So we suspect the difference here is due to the MCMC algorithm is not actually converged. So there is some sort of the thing going on. Yes?
I have a question. I mean, just maybe for other people too, is that, like, when you say true discoveries, like you implant causal SNPs, right? You implant some causal SNPs, and then your method predicts a certain number of these are what I think are the causal SNPs, and then that's the ROC curve you're drawing, right?
No, it's just basically saying they pick the right block, not the right SNP. As long as they pick the right block, I will say they get right. I don't have, so at the SNP level, I think I have an argument, there is no way you know the truth. So I completely gave up, like saying there's a true causal SNP at the SNP level. But at the signal level, again, you can have like very strong confidence on the existence of, in this case, is the signal, the cluster is artificially construct. And then there's every method, you just add up all the SNP level PIP, you get the signal level PIP. So to answer your question, I think you are absolutely right. I would completely agree with you that there is no way to distinguish the right or wrong causal SNP, but still you can, in this case, I'm trying to illustrate, there is a way, there is kind of a strong statistical evidence, at least in the simulation, to pick the right locus.
So what if, I mean, how would it compare to a method if you just take the maximum p-value?
Here you go. That's this one, the purple one.
That's the purple one.
Yes, that's a single SNP, and then just pick.
And the main reason is because you can have have more than one causal SNP in the region?
No, I think it's, well, I shouldn't say no. Maybe you're right. In the region, it depends on what do you mean by region. In the block, it's only one. So, yes. So the reason of this is because it's actually related to that the estimation of that the tau parameter. So if you're just picking one at a time, you always overestimate the residual error variance. So your signal noise ratio is always lower than multi-SNP analysis.
Oh, I see. It's because when you fit all of them together, then your noise goes down.
Yes, exactly. So, yeah. So that's my kind of a main explanation for.
One more question is that you only have 91 regions, right?
Yes.
So then why is your...
No, this is repeated like 1,000 times. So there's across many, but it's using the same LD structure. Yeah, that's right. Yes. Good question. Sure. Yes.
The block size influence the strength of picking the region as well. If you are saying the multiple SNP one is better than the single SNP one, does it mean like the LD block has more SNPs in LD, and then the signal also be stronger?
So they are relatively. Well, I mean, the artificially constructed the blocks have the same size, but within the block, because they're real data, they have different kind of LD structure. So we have no control over these. To answer your question, we don't really trying to favor one block versus the other, or when we pick the signal, it's just randomly put into the block. Yeah, there is another question. So
could differ despite there being some latent causal variable. So in that sense, a fixed p-value might not necessarily reflect as well as like the standardized posterior.
So I'm not sure to your answer to it, but I think my understanding is we're simply just compare the ranking, right? I mean, ROC curve is always just the ranking. So even you don't have normalized the thing, it's just saying this method is more realistic than the other. So I don't know that the normalization itself shouldn't be the thing that changed the ROC curve. Yeah. So the other thing we did for this is so-called calibration, sorry. The calibration analysis, I should really get fast, otherwise we're just stuck in the first one. Nevertheless, I won't tell you what we did. So the Bayesian thing is people like always critical on if your probability is a reliable one or not. So the theory says if you have a lot of observations from the Bayesian posterior probability, it should have frequentist property. So this is the thing. So you can group all the SNPs around a certain frequency bin, right? Because it's a simulation study. So this one, for example, is all come from 40% to 50%, and actually compute how many SNPs from this bin, the frequency of them being really causal SNP. So this is probably directly kind of address Eliezer's first question at the SNP level. So if you have a calibrated approach, everything should be on this line. And then this is basically the DAP-G using the sufficient summary statistics. So this one is the DAP-G using the z-score. You see there's a few points off the line, but they're in the conservative direction. And then this is the fine map. So what happens is you have this counter kind of a conservative approach. This looks like the SNP is stuck in the MCMC and it's not moving, and then they artificially get overestimated posteriors. So that's another evidence. And then if you do FDR control and then you do you get the same result. I should really kind of run to. So this is this is the software if you're interested in. And then this is we run on the real data. One comment is this is a GTAC data V6 versus V8. So you do see the promise of the GTAC. I mean, I'm not really here to advocate for GTAC, but I'm actually advocate for like larger sample size for molecular EQTL study. So this is trying to say there's the biggest the difference between this is the sample size is doubled, the same tissue. And then you see you definitely find more EQTLs in the new GTAC data, and then you find more genes with multiple EQTLs in the cis region. So I really actually love to talk about this, but apparently there is no time. But I would say how do we integrate EQTL result to GWAS? I think Bogdan did a terrific job, so I really don't need to talk about this. There's a TWAS. The second point is colocalization analysis. I was just trying to say, they actually have the same sort of a causal inference if you think about this Mendelian randomization. So there will be the null model, the G will be instrumental, and then X will be the expression, Y would be the complex traits. The null model says there X and Y, there's no causal relationship. And then the alternative causal model say there is a causal relationship. So in graphical model theory, you know how to distinguish these two models, right? How? It's very simple. So this is a kind of a collider structure. If you do this G and then Y, G and then Y, this G and then this Y, they should be uncorrelated. But in this case, G and Y associated. So if you can prove G and Y associated under this causal assumption, then you make your point that potentially there is a causal link between X and Y. So actually, colocalization, if you believe this whole kind of a parenthesis of this whole thing, then you should also believe colocalization is also give you this kind of a causal implication. But there is one more thing. I think it's in favor of colocalization analysis. It can distinguish this kind of a situation. You have two correlated SNPs, and then there is no causal relationship. One SNP is related cause Y, the other SNP is cause X. So this is really hard to distinguish unless you address LD. So I'm just saying there's the results we have make it colocalization analysis make easy. And then this is the software. This is actually my last page. So what else I want to say? If you do colocalization, you find much less. This is a much harder problem. So work on TWAS. So it's a summary slide. So this is this thing is trying to say. So we're trying to deal with a problem. I think we as an analyst, we could be more probabilistic, maybe more Bayesian, and then we need to be more practical. So the on-the-shelf tools maybe not work. Like if you're using MCMC, it may not be the best solution. And then be mindful of a computation. Oh, thank you very much for your attention. Yeah.